Hi again. So now I'm going to present SpaceState, Ad-Hoc definition and identification of hierarchical room states for smart environments. My name is Andreas Fender, and the co-author of this work is Jörg Müller from University of Bayreuth. All right, so first about the context. So imagine you would want to design a spatial user interface, projection mapping based spatial user interface. For instance, like in that case, a teleconferencing system. And now what SpaceState allows you to do is to design that interface for different room layouts. So you have, as a designer, you have full control where is stuff displayed depending on how the room is used right now. Like, for instance, for a meeting versus just someone working alone, and so on. And before I'm getting into any details, I want to briefly talk about a previous work. And in particular, I want to talk about some common assumptions of previous spatial user interfaces. And in particular, often these user interfaces assume a static environment, and more importantly, that there's one purpose per room. So for instance, in Room Alive, it lets you carefully calibrate projectors to project content onto like calibrated surfaces. Of course, it has some automatic features like planar surface detection, stuff like that, but it does not let you design stuff by purpose, but only by room, for instance. And then sort of similar work by Xiao et al., which is called WordKit, where users can actually create interfaces ad hoc, just very quickly, but still when they now move stuff around or switch to a different purpose, then they will have to recreate their user interface. And while the system can detect whether or not certain surfaces are present, it does not detect what is the current use of the room. But the problem here is that rooms can have multiple purposes and hence can also have multiple arrangements. And this is also supported by modern furniture for home or office environments. So for instance, on the left, we can see that we can see the same furniture in the same space, just rearranged, just made possible by that sort of modular furniture. And similarly, in office environments, there are also companies providing modular furniture to quickly rearrange the same space depending on how the space is used. For instance, on the top is for working, or on the lower part is for having guests or meetings or whatever, and it's still the same space. And so the challenge here is that arrangements have different meanings. And so it's not enough to automatically align the virtual content that you maybe design or that you have for your physical space, but instead the meaningful content needs to be designed for each arrangement and for each purpose. Now the question is, like, how do we provide tools for designers to design such spatial user interfaces which are then adjusting to the purpose and to the meaning? And so here's where SpaceState comes into play. So the idea here is that you can just capture a new state very easily by just pressing a capture button. And then from then on, the system will just detect which state is currently active. And then you can, for instance, assign content. And for that, I would like to go step by step through how you would actually do that as a designer. So at a slightly slower pace, I will now explain how you actually use the system, how you would design something in it. And for that, instead of looking at a complex example with a complex room, we will look at a very simple example where it's just about one whiteboard being at a certain location, and we then just use that as as a placeholder for a room state, so to say. So let's say we want one UI widget when the whiteboard is placed on the left, and for that we just add a state identifier, and then we capture and add a new state simply by pressing that particular button, and then we name it. So it's maybe a bit hard to read in the back rows, but it says whiteboard left. And so now we have one state for where the whiteboard is right now, and then we can add content to it. And again, very simplistic example, we would just project a small grid on the whiteboard. For instance, if you want to draw like a graph or a coordinate system, then you have a small projection to just support you with that. But again, the content right now is not that important. And so now we want to have different content when the whiteboard is at a different location. So we just move it to a new location, and then we just add a second state. And then similarly, we can name it. In that case, just says whiteboard right. And again, similarly, we just add content, and in that case, we will just add a browser window, for instance. Again, so the example of all does not make a lot of sense right now, but it's just for as a simple example. And then we can see, it's not really visible in the video, but the upper right part is actually a browser window. And if we now, as a user of the interface, switch between these two, then the user interface will always switch to whatever was designed for that particular state or position or whatever. And now when coming back to like different purposes of the room, so that can be seen as maybe like a work purpose, but if we now say we also want to support some like entertainment purpose, so we assume that we want to have some sort of like cinema setup when the whiteboard is over there. So we just create a state for it, and please ignore the typo here. So it says cinema, and then similarly we can just project some cinema browser window over there. And so yeah, so that's what it looks like over there. So whenever the whiteboard will face the couch from now on, it will switch to that cinema mode. And as you can see, it's very like kind of fast to create these interfaces, and then otherwise you do the rest just in Unity as you would always as a designer of such interfaces. And now like a little bit more elaborate examples. So now imagine we have our 3 states, and now within one of the states we want to further distinguish where the user is located. And then we basically do the same, just like one level deeper, where we add another state identifier within our whiteboard state. Then we say, okay, person is left. Then we ask the person nicely to move to the other side. And then we make a new state, person right. And in that example, instead of adding content, instead of adjusting content, assigning content to it, we want to assign transformations, and here's how it works. So you basically just move the window to the side where you want it to be, and then when you're on the other side, you move the window again. And as we can then see, if the person is like moving left and right to switch states, then the transformations are just adjusted. And in that case, it can, for instance, be used to avoid the content being blocked by the shadow or something by always moving it on the other side. Okay, so these were only some simple examples, and now I want to talk a bit more in generic terms of what kind of state systems you could build in SpaceState. All right, and in particular, I want to focus on independent states versus hierarchical states. And so here's an example for independent states, which is, again, pretty straightforward. So it basically means that you have state identifiers which just coexist, and so that whiteboard location, for instance, is completely independent of whether or not the drawer is open. So very, very simple example. And then on the other hand, you can have it hierarchically, where you just drag one of the state identifiers into one of the other states. And now what that means is that it's only going to be active whenever the superstate is active. So only now the drawer will be checked. And in more general terms, so you don't have to understand all of it right now, but it's only to show that it can be nested or being independent, like on any level. So, okay. And now briefly about the algorithm. So obviously there are a lot of more details in the paper, but I want to briefly sketch what happens when you capture a state and how the system would then actually identify it. So whenever a state is captured, obviously we're going to store the point cloud, but on top of that we're going to store a 3D voxel grid, and that one contains a score function. And again, the details are maybe not super important right now, but it basically means like the closer a voxel is to a surface, the higher score it has. And that little visualization on the right is just a transverse section, so it's projected back to 2D, but I hope you get the idea. So that's just a 3D grid containing all the values to the closest distance, to the closest surface point. And now here's how the algorithm works. So now imagine, again, we look at it in 2D. So that's like a whiteboard from the side, for instance, the blue captured whiteboard. And now let's say we have 3 points which are captured right now. So these points do not really depict anything right now. They're just right now just captured, could be points from a person or something. And so what we do now for each of these captured points within each of these voxels, we just assess how far away is it from a captured voxel. And right now I'm just going to display it in voxel units. But of course, in the end, it's actually the score function which is being evaluated here. But for now, we just say it's 5 because it's 5 voxels away. And instead of storing it in the actual point where we found it, we actually store it on the captured surface. And then we do the same here. And now here, it's the important thing here is that we only store the lower distance. So in that case, the one with 3 is closer to it. So the occupied voxel on the blue line is going to be 3. So that has some properties, some like nice properties to do it like that instead of just counting voxels and how close they are in general to the captured surface. So in particular, let's just look at some examples. So for instance, if the user is not exactly aligning the furniture when the state is being set up the second time, so this is just like a screenshot from our evaluation, then of course simply counting voxels or checking whether they're like inside each other, whether they're inside the captured area is not enough. So you need to do some more to actually be robust towards some like misalignments. And so the way the algorithm is doing that, again, is by storing the score on the captured voxels and not on the current captured point clouds. So for instance, if a whiteboard is kind of close to the captured whiteboard, then it will get a very high score because all the points are contributing to that overall score. So it's all getting like 3, for instance. Whereas if you have something else standing there with a lot of voxels, which are kind of close, but still only very few would actually contribute to the overall score. So this one would not be detected as a whiteboard standing there, for instance, simply because all these other voxels do not really influence the score. But again, if it's not completely clear, you can just read the paper in that regard. And another very important part, so far that was only like how do you calculate like the current state like right now, but also the important part is how do the states relate to each other. So if you have multiple states, then there has to be some sort of weight function also to assess how much influence has a voxel. So for instance, that's like, again, a very simple state system where on the lower part we can see person left and person right, and then we can see these green, oh, I can see my cursor. You can see these green clouds of voxels and another kind of greenish cloud. And so what happened here is that the system detected that, for instance, in the middle, these voxels do not really help for distinguishing whether the person is left or right, and therefore only these voxels are actually having an influence on the score. And then similarly, when they're independent states, they actually need to remove voxels from the other states, so they sort of compete for voxels, so to say, so that they don't disturb each other. So the table, for instance, should not disturb whether or not the person is standing left or right, and therefore the weights, like according to the weights, some of the voxels are removed from other states, and so on. But again, like a lot more detail in the paper. And then optionally, if the designers wish to do so, they can activate like an automatic content alignment. So again, because states will not be aligned the exact same way the second time, that also means that the content might not be projected correctly. Like if you misplace the whiteboard, then the content might be a little bit off. And therefore, pretty straightforward, we just use an iterative closest point algorithm to then also align the contents. And to quickly go through an application example, so I already showed it in the beginning. So imagine you have a remote teleconferencing system, and now with SpaceState, you can design the arrangements for each physical arrangement. And here's the state system. I won't go through all the states and substates, but just like in general, the way it works is that we have some remote video, and that one is being streamed and forwarded to whatever state or substate is currently active. And so these streams are actually handled by the web framework presented last year at ISS. But now for SpaceState, the interesting part is, of course, like which of these are active and what does the content look like when the states are active. And for instance, if there's a coffee break, then there's no projection or anything. So and it's also not possible to call in. If the state is in a work state, so if someone is just working alone, then we have different substates where the person is in different locations relative to the whiteboard, and then the projections are adapted accordingly. And then there's the meeting setup, where it's either just projected on the table as a small video patch, or if available, it's projected on a big whiteboard. And here's like a quick fast forward how it looks in action. So on the upper left, we can see the point clouds, and then the respective states which are active in these moments. All right, so to quickly conclude, so SpaceState allows designers of spatial user interfaces to create content which is mapped to the state and the substates of the physical room. And that content can be projection mapping, as shown in this presentation, but it, of course, is not limited to that. So it could be AR and VR content, could also be music and sound effects and stuff like that. And so the system identifies the current state and the substates of the room in real time, and it organizes states hierarchically and or mutually independent. All right, so with that, I would like to thank you, and I'm open for questions. Thanks.
Thank you. Questions?
Hi, Patrick from the Interactive Media Lab, Dresden. Nice work. I was wondering if you thought about continuous transitions between states. For example, if I have something when I'm on the left on the wall and something on the right on the wall, when I'm on the right on the wall, can I have it following me around? Is that possible?
Actually, I partially implemented that. Like in some early versions of that was actually featured. But in the end, it was more like a matter of focus, like kind of let's focus on these like kind of easy to understand discrete states. But in the end, since it's all like about score functions, you have like floating numbers between how much a certain state is active. So you can sort of interpolate between states. So you kind of have the numbers for that. They're not like entirely linear. So it's still a little bit depending on how your states are organized. It can be that you don't have very smooth linear interpolations, but in some cases you might. But it didn't so right now I didn't really look further into it because I just wanted to focus on the states itself. But in general, yeah, it's like a very interesting thing to also look at. Yeah.
Yeah, Fabrice Matulik, Preferred Networks. Yeah, I like this work too, and I was wondering how you would address the issue of discoverability, because you basically you have very complex state hierarchies and configurations. So do you suppose like people who are not familiar with what's possible with your system, would they just look at your interface and understand what objects they need to move and where they need to position them, or would you be envisioning some kind of projection system that will tell you if you put the panel here, you can go into cinema mode, or I don't know. Have you thought about that?
So you mean that the users will maybe not necessarily know which states exist in that space?
Yeah, so they like the meeting room, right? You have a meeting and you're not familiar with the equipment, and people who enter this room for the first time they don't know what they can do with the equipment. Or in this case, the furniture, how they should position it to have all these possibilities, all these configurations. So
in that case, it's again a matter of use case. So in the Envision case, it's a very like designer in the loop thing, where a designer would be like in the space, would kind of see and interact also with the people using that space seeing that they're having these configurations like already, so they are going from meeting to meeting. That's how they set it up. So that it's not necessarily the designer deciding what kind of different configurations exist. It's more like these purposes are already there, and the people are already using the rooms in different ways. And then a designer would just support that by such a system, for instance. So right now there's no like help in guiding users how they would need to configure stuff to, I don't know, access certain functionalities. The hope is that they would just configure it because they want to, because right now they want to have a meeting, and then the system would just switch to that particular mode, for instance.
Hello, very interesting talk. Philippe Jourdaud from INRIA. How user could interact with the system? For instance, in your use case, it's a Skype. So how they could start a Skype or stop a Skype or add someone? Do you thought about that?
Oh, so you mean the application, like the example application? Yeah, so it's a very, very basic application right now. So it does not really have many like UI elements or anything. But these would need to be added. But that's kind of like independent of the current work, because I mean the framework it's based on it. Of course, it has these widgets where you could like place buttons and everything. But in that current iteration, I was kind of only like implementing the minimal widgets to show the concept, basically. So it's not a fully functional like Skyping app by any means. So I think that would be more like maybe a dedicated future investigation.
Laurent Tevin from LMU Munich. My question was, how do you know, as you already capture all the point or the voxel of the room, how do you know which part is significant for a state, and in particular for a substate? How do you know it is a table that is important, or it is a whiteboard? Because I guess the people just move one element and keep the rest of the room at the same place.
Yeah, so it's basically also pretty simple. So I can try to get back to that slide. So here it's basically what's happening here. So whenever you have multiple states and an identifier, like the way these weights are calculated is really like how do these states relate to each other. And if there are, for instance, voxels which do not really, which are not different among the different states within identifier, then they're kind of disregarded. And that kind of naturally carves out, or it naturally kind of finds the voxels which are actually relevant for the particular state. So in that instance, for instance, it's like the voxels around the person where the person was captured, which are then used for checking the. Mm-hmm. So in the moment, like the very moment of capture, it's not known yet. So first, it's just all captured. You just have these. You have these complete distance functions, and you have multiple of these. But as soon as you put them into the same state identifier, then many of these are just getting disregarded. Like, for instance, if you would now if you make a second state where the whiteboard is like somewhere else, then the distance function would be kind of the same around the couch and around the table, for instance. And then the system would just disregard those, at least like really depending on how these states are put together. So you cannot tell that for the state in itself. It's like you have to look at it like globally.
So, any other questions? So that was the end of today's session. So we really have